This is Precalculus, chapter 14, lesson 4 on page 936. Here we go, guys. Continuity. Page 936. 4. 3 was the formal proofs. You remember?
Yes. I'm sorry.
Okay. Continuity. All right, I'm going to give you the definition. You ready? A graph is continuous, or a function is continuous. This is the simplest definition ever. If and only if you can begin to draw the graph and finish it without lifting your pencil. Right? All right, so if I start here and I can draw it and finish it without lifting my pencil off the paper, then that graph is continuous at every point. In calculus, we look at a particular point. Is it continuous at a particular point in the graph, or that point C? A graph is continuous at a point. I don't really like drawing that circle because that really looks like a hole in the graph. I'm going to draw a point. All right. So we can look at, is it continuous at this point, C? And as long as I don't pick my pencil up at point C, then it's continuous. Make sense? All right, so look at the images on page 936. The top left is continuous at x equals c because it is defined. And the point on the graph is c comma f of c. Make sense? The f of c represents the y value. The c represents the x value. You see that? Top right, it's continuous at that point c because I don't have to pick up my pencil at the point x equals c. Now there is a point where it's not continuous. That top left, top right. It's like the y-axis, right? It's not continuous at c equals 0. Make sense? All right, the bottom one. At C, bottom left, it is continuous. But over here on the left, at this point, it would not be continuous. Because what happens here? I have to pick up my pencil and move, right? But if I'm looking at point C over here, it is continuous.
But the line itself, or not the line, but like the graph itself is not.
The entire function is not continuous. At point C, it is, because I do not have to pick up my pencil. And the same with the bottom right. It is continuous at C. All right, now look at the top of page 937. These are examples of discontinuity. All right. So look what happens on A. These are actually labeled. The ones on the bottom are not labeled. At A, when we get to C, here is C. I have to lift up my pencil because there's a hole in the graph. So what do we know about C if there's a hole in the graph? It's discontinuous. And what causes a hole in the graph? What causes us to have a hole in the graph? A 0 of the denominator that is also a 0 of the numerator. So you'd have, I don't know, x plus 1, x minus c, x plus 5, x minus 2, x minus c. This means there is a hole in the graph at C.
And you can't cancel those.
Okay, we're going to talk about that in a minute. You jump ahead. It's called a removable discontinuity. All right. A limit does exist with removable discontinuities. Okay, but that's in a minute. Got it? All right. B, here's C. It is not continuous, right, at C because I have to lift up my pencil. This is called a jump in the graph. When there's a jump in the graph, typically we have something like one formula, x squared, I'm just making this up. If x less than or equal to c, and then it would be x cubed plus x minus 5, x greater than c. We would have a piecewise function when we have a jump in the graph. That is typical. We also would have a piecewise function when we have a hole in the graph sometimes. So you might have f of x, I don't know, x to the 5th minus 5 when x does not equal c. And then you might have c, well, let's put f of c, f of c, f of c, that's your y value, right? When x equals c. So they might plug it. This is when they're plugging those holes, but they're not putting it right there. Something happens there. There's an anomaly. All right? So you can't have a piecewise function if you have a hole in the graph. God bless you. All right, look at C. What do we have with C? We have a vertical asymptote. When do we have a vertical asymptote?
0 at the bottom.
0 of the denominator. That is not a 0 of the numerator. All right? And then D. We just have a hole in the graph that hasn't been defined. Hadn't been redefined to make it another place. So all of those, A, B, C, and D, are all discontinuous at the point C. Does that make sense? Why do we look at continuous versus discontinuous? Because the continuity tells us the behavior of the graph. Or if it is discontinuous, it tells us we can look at the behavior of the graph around where it's discontinuous. We can use calculus to see where there are holes. We can use it to see where there are asymptotes, vertical or horizontal asymptotes. We can look at the behavior of the graph. We can say, is the behavior of the graph going to positive infinity, or is the behavior of the graph going to negative infinity? Because once we get our asymptotes, let's say that's a horizontal asymptote, that's a vertical asymptote. We want to ask ourselves, what happens around this horizontal asymptote and what happens around this vertical asymptote? Maybe it looks like this. The graph looks like this and like this. Because you know that the graph approaches those asymptotes, but we don't know if it's here or if it's here. But we can use those asymptotes and that discontinuity to look at the behavior of the graph. So that's why we look at continuity. All right, so we can look at continuity at any point on the graph. All right, so turn to page 938. Look at the top image. So one of the images has the point in the middle of the graph. That is C. That's an interior point on the graph. The other one has it at an end point. C is at the end point. All right, so we can look at limits coming from the left and the right. All right, so this would be continuous from the left and the right. But this one would only be continuous from the right. All right, so how do we look at that? We can look at a limit as x approaches C from the left. You see that? Or we can look at limits as x approaches C from the right. So we can look at continuity at an interior point, or we can look at it from the left or the right to see what is happening to the graph. This is important because of our asymptotes. We want to know what happens to the graph as we approach that asymptote from the right. That's there, from the right. And we want to know what happens to that graph as we approach that asymptote from the left. Yes?
So the C plus, is that just saying if I come in from the right?
This says from the right, this says from the left. You just think a number line. The left side of a number line is negative, the right side of a number line is positive. For both of these, if I plugged in f of C, would it be defined? For both of these images? Yes. Why? Because they're points on the graph. So a point on this graph would be C comma f of C. That's just simply your x coordinate and your y coordinate. All right, so look right under continuity at an interior point. It says if the point CF of C, which is just XY, is an interior point of the graph, and the graph can be drawn around that point without lifting the pencil, then at the very least this must be true. F of X is defined where X equals C. And f of x must be defined for any number near C. All right, that's this one. So it says this one must be defined and numbers ever so close to it are defined in the graph. All right, and then at the bottom is this image. If f of C is defined, then there are two conditions that can prevent a function from being continuous. Two things that prevent a function from being continuous. This is at the bottom, the two bullets at the bottom of page 938. Two conditions that prevent a function from being continuous at a particular point. If there's a jump in the graph. All right, so it is not continuous if there's a jump in the graph. All right, here's a jump. Here's a jump. It's like we're jumping across the y-axis. This would be a jump. We jump from negative infinity to positive infinity. All right, those are all jumps. So any jump in the graph causes a function to be discontinuous at that point. If C were in here, if this were C, if C were in here, between them. All right, jumps in the graph. The second one is holes. If there is a hole in the graph. All right, but there's a difference between a jump, okay, I'm gonna label these, jump and a hole. All right, so this would be a hole in the graph. If there's a hole in the graph, a limit does exist. Is there a limit? Yes. There is a limit at C. Because what does a limit ask us? What does y approach? It doesn't ask us what's the value of y at C. So from the left and the right, we're approaching the same value. Here, from the left and the right, we're approaching different values. Definitely, that's infinity. Infinity. This would be infinity, except lesson 5 is infinite limits. All right, so with holes, a limit exists. Until we get to chapter 5 with jumps, this really is the only case where we don't look at limits. Here, this kind of a jump. This would not be a limit because this is approaching negative infinity and positive infinity. We're going to look from the left and the right for this one. This one we could say both are approaching infinity. All right, so does that make sense? So look at the image on the top of page 939. I'll try to draw it. And let's look at each one of those points. All right, that's A, that's B, and that's C. All right, we know at A, that's a 0 of the denominator, that's not a 0 of the numerator, right? Because there's a 0 of the denominator that is a 0 of the numerator, because that's a hole in the graph, right? So, we'll say f of A is not defined, but does a limit exist? Yes. Okay, so it's not defined, but we do have a limit. All right? At B, f of A is defined right here. I'm in B. This is B, Paula. Right here. Whatever that is on the y-axis. All right? But does a limit exist? No. All right? And in this case, it is defined right here. F of C is defined, but it doesn't equal the limit because the limit is going to be right here because we look from the left and the right. So F of C is not going to equal what your limit is. So 3 different instances where either we do have a valid output or we don't, and a limit exists or it doesn't. Make sense? So far? Okay, so can we really decide, are functions continuous? I do want us to look at that box. I have it asterisk. All right, so it says let f be a function that is defined for all x's in some open interval containing c. Then f is said to be continuous at x equals c if the following conditions are true. If f of c is defined, do you know what that's saying? If when I plug in c in, I get an output y. If the limit as x approaches that c value actually does exist, and if the limit equals what f of c is. Okay, that's none of these. That is this, right? F of c, I plug it in, it exists, right? The limit as x approaches c, it does exist. And that limit as x approaches c does equal whatever f of c is. This is the only case. And this has to be a polynomial. Or we have to be looking at an interior point in something other than a polynomial. Okay, so example 1 is not a polynomial, right? So we know that there are going to be maybe holes in the graph, jumps, someplace where it might be undefined. So without graphing, could we show that this function is continuous at x equals -3? All right, when you just first look at that, do you think that function is continuous at x equals -3? Say that a little louder. Yes, why?
Because there's no holes in the graph.
It doesn't make the denominator equal to 0. Right? All right, so guys, we could just plug in -3. All right, so that would be the square root of -3 squared minus -3 plus 1 over -3 minus 8. That's 9. 9 plus 3. 9 plus 3 is 12. 13. So it's the square root of 13 over -11. -8.
It's -5, yeah. It's -3 minus 5, not -6.
No. Oh, I'd already done it in my brain,
Yeah.
huh?
You're just in that.
-8. Yeah. So that would be negative square root of 13 over 8.
We're gonna rationalize the numerator.
I would leave it. So, do those three things happen? Is f of c defined? Yes. That says, is f of -3 defined? Yes. It's negative square root of 13 over 8. Does the limit of that function as x approaches -3 exist? What is it?
Negative square root of 13.
Yes, negative square root of 13 over 8. Does the limit equal the f of x? Yes. Tress?
I'm sorry, but like, how do you know that is the limit?
Okay, how do I know that's the limit?
Is it because it's not like a piece, function? Or
This is not a piecewise function. No, piecewise function has different, yeah. What, go ahead.
Well, I was just gonna ask, we just have to know it's defined and that shows it's continuous, like that's the only thing.
As long as you don't have a piecewise function. And do you know what the square root looks like?
Vertical.
Yeah, well,
The V?
you know, it looks like that. Or it looks like that. But it's been shifted around. All right, so it is continuous at x equals -3. All right, look at the bottom of page 940 in the box. Let's go through those together. We have special functions. Okay, every polynomial is continuous at every real number. You knew that already because if you have a polynomial, that means you have nothing under a radical, no x under a radical, not nothing under a radical, no x under a radical, and you have no x in the denominator. Every polynomial is continuous. The sine curve is continuous. The tangent curve is not continuous. The cosine curve is continuous. Any cubed equation is continuous. All square roots, all lines, they're all continuous. Every rational function, okay, I'm on the second one. Rational function, that means there's a ratio of polynomials, okay? Is continuous at every real number in the domain. The domain is all the possible x values. For this one, this function is continuous at every x value except x equals 5. X equals 5 is not in its domain. Domain is your possible x values. Got it? Okay. Hang with me one more time. All right. So this is where it would be discontinuous, right? When would this equal 0? Okay, it's only when the numerator equals 0. Okay, I'm going to write this out separate. Okay, y'all look. When will this equal 0? When what's under the radical would equal 0. Okay? Because when the denominator is 0, it's undefined, right? Okay. Every exponential function is continuous at every real number because the exponential function either looks like this, that's exponential growth, that's exponential decay. All right, look at logarithms. Every logarithmic function is continuous at every positive real number. Because this is what the log function looks like. So it's only positive x values. All right. The sine and the cosine are continuous at every real number. The tangent is continuous at every real number in its domain. What do you remember about the tangent? Where is it discontinuous? At every odd half pi. Every odd half pi. All right, let's look at continuous on an interval. All right, so we're talking about from the left and the right. That's continuity on an interval. I already talked about that a little bit. We're going to look from the left and from the right. So I'm going to draw some images. All right. Is B continuous from the left? Yes. So a limit as x approaches b from the left exists. It's defined. Is it continuous from the right? No, it is not. All right, what about well, I could just draw another one just the same. All right. So we're going to look from the left and the right. Now, that's in the box on page 941. A limit is continuous from the right, provided there is that BF of B. It is not continuous. A function is continuous from the left as long as it's defined. So this would be continuous because when I plug B in, I get that output. This is not continuous because when I plug this value in from the right, I get this output. It doesn't equal there. Make sense? All right, so let's look at example 2. The function is, so is it continuous from the right at x equals 0? From the right, the limit as x approaches 0 from the right. Is it continuous? Well, can I plug in 0? It equals 0, right? It's defined, and therefore the limit exists. Make sense? Because it is defined. But what if I were coming from the left? What do you know about this graph? Could I come from the left? Okay, but we do know. I just need to, because you should know about this graph. Square root of x starts at 0.
And this one, just like a point there.
And goes this way. So from the left, it's not defined. It's only defined from the right. Got it? We're going to get some. All right, let's look at example 3. All right, we're going to discuss the continuity of this function at example 3 on page 942 at x equals -3 and at x equals 2. And then we're going to give intervals on which this function is continuous. All right, so is it continuous at x equals -3?
No.
It is not. So below x equals -3, what is the range on which it is continuous? The interval.
Like, greater than -5 to less than -3.
That's interval notation, right? The parentheses means not equal to. Okay, what's the next interval on which it is continuous?
-3.
So it includes -3, right? All the way up to +2. And then it goes from,
2.
but not equal to 2, to infinity always goes with a parentheses. So the 2 points right here is where it's discontinuous. At x equals -3, at x equals 2. Make sense?
What do you mean by discontinuous? You mean like where it breaks off?
Discontinuous means I have to lift my pencil.
Okay. That's what I thought.
Yes. Now, I didn't draw it. But this part in the middle, it's continuous from the right here. It's continuous from the left here. But if I'm going here, is it continuous? It's not, because it's not defined. All right. Okay. Look at the top of page 943. The same properties for limits that we talked about are the exact same properties for continuity, all right? If two functions are continuous at every point, then the sum of the functions are continuous. Then the difference of the functions are continuous. Then the product of the functions are continuous, and the quotient of them, as long as the denominator doesn't equal 0, right? Okay, so we're going to talk about the continuity of two functions, all right? All right, so look at example 4. We're getting close to the end. It's a good thing. All right, is the sine of x continuous at every point?
Yes.
Come on, guys. Y'all know what it looks like.
Yes, it is.
It is. Is x cubed plus 5x minus 2 continuous at every point?
Yes.
Yes, because it's a polynomial. So is the sum of them continuous at every point? Yes. Okay. Look at B. Are those continuous?
Yes.
Yes, because the sine is continuous and x cubed is continuous at every point. Therefore, the difference is continuous at every point. All right. What about the product of them? Are they continuous?
Yes.
Yes, they are continuous. Because they're both continuous. What about the quotient? As long as x cubed plus 5x minus 2 doesn't equal 0, then they're continuous. Got it? That's all that one is asking. All right, let's do the last one. We're not doing the intermediate value theorem. All right, so let's do the last example. All right, can we... Okay, do you remember composition? Composition, guys. God bless you. Composition is written this way, right? We plug one function in to another. All right.
That function is the G into the F function, right?
Okay, so h of x is a composition of functions. So could we come up with some functions that it's the composition of? Is it continuous at x equals 2?
Yes. I mean, it says so. Oh,
It says so. We could plug 2 in and see if we get the answer. But could this be, what are some options of this being the composition of?
So G. Then you could have the square root.
Wait, do you mean that square root goes
And then
into
you
it?
could have x cubed minus 3x squared plus x.
Right. So this would be f of g of x equals h of x, right?
Because if you do
Right.
you'd be putting G.
You plugging this one here. Okay.
Which is the same.
All right. Now, we want to know if it's continuous at positive 2. Is the square root of x continuous at positive 2? Yes. Is this continuous at positive 2? Yes. Therefore, the composition is continuous.